not going to play this.
Okay, so we're starting new stuff today. This is a really important unit. This is a good one. This will be, most of this stuff is going to be, I think, pretty new to you, this unit. So we're starting to get into that part of the class where, you know, not much of this is going to really be review anymore. We're going to do a couple odd, kind of disjointed things at first that are important and will all make sense. But then what mostly this unit's going to be about is parent functions and transformations. So our goal is, by the end of the unit, what you're going to be able to do is you're going to be able to know what a bunch of parent functions, what the basic graphs look like. And a bunch of you already know. Like if I did something, so we should get earbuds and phones and all that stuff away from you. We should have good knowledge of, like, if I were to say, what is the absolute value function? You would know, after we talk about it, you're going to know that that looks like a V, right? Where the vertex is at the origin, that's what the parent graph looks like. You know what the parent graph of y equals x squared looks like already, right? What's that? Just describe it for me. Okay, so yeah, parabola, right? Where's the vertex? 0, 0 at the origin, right? And we'll talk about some of the characteristics of these parent graphs. And you're going to be able to, like, we'll do a little quiz where you'll just have to be able to sketch all the parent graphs, you know. But it's easy. You'll know, there'll be some other ones too. The point of this, though, is once you know what all those parent graphs look like, and you know the transformation rules, you'll be able to take those parent graphs and tweak them in a bunch of different ways. You'll be able to translate them around the XY plane. You'll be able to stretch and shrink them vertically. You'll be able to reflect them over reflect them vertically so they open, like the parabola opens down instead of opening up. And you'll be able to do a bunch of things to the graph, a bunch of transformations to that parent graph based on the transformation rules we're going to study. So that's where we're going this unit. It's not a real long one. We'll get through this pretty quickly. But we're starting off with just introducing some new functions that you haven't really ever seen before. Okay, and this doesn't really relate to the translation stuff. It just kind of falls under this unit because they're new types of functions that you're not familiar with. And the first one is really a class of functions that we deal with a lot. We deal with like these a lot in calculus, for example. A piecewise function. So a piecewise function is it's a function that's made up of more than one function. Each with its own domain. Okay, so we're going to look at graphing these here in just a second, but let's go at this first by looking at just evaluating these functions. Okay, kind of get a feel for what this means. So this is how they look pretty goofy. This is how we would write a piecewise function. Have you ever seen something like that before? No? Okay, that looks a little strange, right? So when you have a piecewise function, the way we write it, we write f of x equals, and then we're just going to do only the left part of a script bracket. And that's kind of our sort of our code in math to mean that there's going to be more than one piece to this function. And then each row to the right of that symbol, we have one row for each piece of the function. So we could have a piecewise function with 2 pieces, or we could have a piecewise function with 3 pieces or even more. Okay? And then so you get f of x equals, we can see that we've got 2 pieces to this function, and then next to each function, to the right of it, usually there's a comma. We don't usually use the word if, but in these worksheets, like when you see this stuff in Moodle eventually, if we do any of this on Moodle, I'll put commas in it instead of ifs. Okay, but either way, to the right of that, you're going to see the domain that goes with that function. So what does this piecewise function really say? It says f of x is equal to x squared minus 1 for the domain x is less than -2. And f of x is equal to the different function 5x plus 3 for the domain x is greater than or equal to -2, right? So there's two different behaviors in the function. It switches gears based on which values of x you're inputting, okay? So let's look at evaluating this piecewise function for a moment then. What if we want to evaluate this function at -5, f of -5?
Then you just plug in 5 to x, -5.
Okay, you're gonna plug -5 into x, but the question is, which piece? Because there's more than one option, right? What do you think, Jordan? Which one? First one, how come?
Because on the bottom one, it's -5 is less.
Okay, good. So -5 falls into the top domain, doesn't it? Right? And so therefore, that's the part of the function that's active when x is -5, right? So for part A, then, we would just do this. We would say that f of -5 is going to equal, remember how we evaluate functions, right? This is good technique. We always want to open up an empty set of parentheses, an empty quantity, wherever there's a variable. So we have an x squared minus 1, and what's the value we're plugging in? -5, right? And so what would that equal? -5 squared is 25 minus 1 is 24. Okay, so 24 would be the value of the function at -5. Okay? What about at -2? Now, just don't say anything out loud. Everybody look at that for a second.
So wait, the first one, that would just be our answer.
That's your answer, right? And what's that mean then? So that means when x is -5, what's the value of y? 24. That's the output, right? When the input is -5, the output's 24. And so we could, if we wanted to, we could write that result as an ordered pair. We could write it as -5, 24, right? Yep.
What is the purpose of piecewise functions?
So piecewise functions are really valuable in real life because a lot of times a function that's modeling something in physics, for example, is gonna change based on the inputs. I'll give you okay, here's an example. Like what if a person were you're gonna be charting a person's height, okay, above like sea level, for example. And so you're gonna have this function, y is a function of t, where y is the height above sea level and t is the time, right? So the person is he's climbing up a ladder, let's say, he's climbing up a ladder and walking onto a diving board and then he dives off the diving board. There's gonna be different pieces of that function that are gonna be modeled in different ways, right? When he's climbing up the ladder, the function is gonna be that, his position's gonna be changing slowly with time at a constant rate. Right? I'm not going to put the specific equations up. Did everybody get that? You're walking out the horizontal diving board, so for another period of time, the height is not going to change, right? So there's going to be some period of, some domain, some time interval from t equals something to t equals something, where the height is the same. And then he jumps off the diving board, and he's going to accelerate towards the water, and so it's going to be a different kind of, right? So there's an example of a place where we would want to model that situation with a piecewise function, because there's 3 different things going on. Okay, good question. Okay. Give you another one real quick. Like, what if a person were skydiving? Let's say you're skydiving. You're jumping out of a helicopter. You're skydiving out of a helicopter. It's really high, right? So the first part of the function, you're just standing there trying to get your nerve up, right, to jump out of the helicopter, and so your height is fixed. You jump out of the helicopter and you're going to accelerate for a while, but eventually what happens to you when you're in free fall? You hit terminal velocity, right, where the air resistance upward matches your weight downward, so you're going to fall at constant speed for a while, and then you pull the chute and something else happens, right? So once again, you need a piecewise function to describe that accurately. Okay? All right, so what about -2? Now look carefully at that function. Is it going to fit into the top or the bottom? Bottom, how come? Okay, good, because the bottom piece includes the value -2, right? So we would say then that f of -2 is going to fit the bottom behavior, so it's 5 times -2 plus 3, which is what? -7, okay? And then finally, what about f of 7, top or bottom? Bottom, okay?
38.
So f of 7 would be 5 times 7 plus 3, which is 38. Okay. So now let's talk about, and we could do, we could do this again with this bottom one. You just tell me. We don't have to do the whole part of this. We could probably skip ahead a little bit with this group. But if I'm evaluating g of 2, which part of the function is that going into? We'll go ahead and do it. Just take a second. We'll do this.
Go into the bottom equation.
Bottom one, everybody agree? Because 2 is greater than or equal to 1. Okay? Say it again.
Oh, wait, sorry.
Yeah, -4, there you go, okay. And is it, if it's a function, can I ask you another question here? If this is a function, is it ever possible that when I evaluate the function at a point, it's gonna be on more than one row at the same time?
No, because of the vertical line.
Because of the vertical line test, right? So you could never have parts that overlap vertically. Pieces can never overlap vertically. So it's only, if it's a function, you're only ever going to be using one row at a time, right? Or one piece of the function at a time. Okay, so g of 2, you told me correctly, fits into the bottom one. So that's going to be 2 times x, which is 2 cubed, plus 9. What's 2 cubed?
8.
8 times 2 is
16.
plus 9 is,
25.
okay, right? What about -1?
-1 is the middle one,
Middle one.
and it's 0.
So we're gonna get g of -1 equals -1 minus 1, so that's +1 plus 1, which is 0. Good.
Minus 1.
And then, what about -6?
-6 is the top one.
Top one? Okay, so
And
we're gonna
it's
get
0.
Okay, we gotta go through the steps first.
1/2 times -6
-3
plus 3, so we get -3 plus 3, which is
0.
0. Okay, is that a problem that we got the same output value?
No.
No big deal, right? That's okay, we can do that. Okay, so now, let's focus on graphing these things, right? And so there's a couple ways, with a high-level class like this, one of the things we want to do is we want to make sure, we want to understand things in multiple ways, right? Because it's all consistent. The more ways the more different angles you can focus on the problem from, the better you understand the problem, right? So what are some things we can do? Now, when we want to graph this function, there's the 2 pieces we're going to graph individually, of course. One way you can think about this, at least, if we're going to graph this top one, let's graph red. So we're going to graph the function y equals -3x minus 7, which is just a line, right? And we're going to graph that in a specific domain. But one thing we could do is we could just get the shape of the line. So I'm going to graph it very lightly, just so we have kind of a template to use to draw the line in our domain, right? So if I wanted to graph that line, how would I graph that line? So I start at -7, okay, so on the y-axis, right? So 1, 2, 3, 4, 5, 6, 7. So I'm starting right there.
And then you'd go left 1 and up 3.
Okay, I'm gonna technically go down 3 and right 1, but we'll reverse that because it goes off the graph. Everybody agree? So instead we'll go up 3 and back 1 to get another point. And then I'm just gonna lightly graph this then. So this is gonna be in just light red. So that's the shape of the line, right? Okay, but where does this line actually live? What's the domain where it's defined?
Less than -1.
Less than -1. Okay, so then that means I can only, when I want to graph this thing, here's a way of thinking about it. I can only actually put my pen down at -1 and graph it to the left or the right of that point.
Left.
Does anybody see that? Because we're only wanting the parts that are less than -1. So I would put my pen down there, and am I going to graph a open or a closed endpoint when I put my pen down? Open, how come? It's not equal to -1, so we're not including -1, but there's the endpoint. Why did I put the dot right there? Because
that's -1.
Because that's the point on this line that we drew where x equals -1. Okay? Everybody get that? So now,
If we did it no one, then we would put it, we would graph it. Move down to the domain. Oh, but it's
You're right, okay, and we could have done that, right, and that's fine, we could have used, so it's coincidental that, I think I understand maybe what you're asking. Why did it coincide with the first accident, right? We could have just as easily gone down by 3 and over by 1 and used that point and that, that point and that point to line up our line. But I'm only gonna start making the graph there. Does that make sense? Okay? All right, so you get that if I graph the equation y equals negative 3x minus 7, that line goes forever, right? And that's the light pink line that goes forever. But this one right here is restricted, right? This is only, its domain is restricted, and so I can only actually make the graph in this piecewise function from this point to the left. Okay? All right, so then what about the other piece? So the other piece is the line y equals negative 5.
So it's just a straight line.
Well, every line's straight,
You know what I mean, like.
but it's just a horizontal line, isn't it? Right?
But
So
that's
it's
not a function.
So it's a horizontal line that intersects the
yes.
y-axis at negative 5, which is right there, I think, right? 1, 2, 3, 4, 5. And the line's just gonna go forever to the left and forever to the right. But,
But it's greater than -1.
yeah, the domain is greater than or equal to
So,
negative
yeah.
1. So we'll put our pen down on the board at negative 1. What kind of an endpoint are we gonna make?
Close.
Closed. And then we're only gonna trace along the line y equals 5 to the right because of the domain. Okay, does that make sense? So there's our piecewise function. We got the red piece and the blue piece. Does it pass the vertical line test?
Yes. Yeah.
Yes.
Undecided at the
No,
moment.
Yes,
that's
it's
just
just
that.
Okay, it actually doesn't it? Because look, even right here, if I,
It's not included.
exactly, so when we graph the vertical line here,
It's been close to almost done.
look, we're good. Right there, we're still good, because the line is only passing through the function at the blue endpoint. The red one isn't there, right? It's an open circle.
Oh, because it's open, right?
Right? So when we're doing this vertical line test,
That is a big one.
that's a major line, right? So the line is only intersecting the curve at one place, and over here it's only intersecting it at one place. The question is, what about at the junction between the two? No, we're fine. Because look, it's the red endpoint is an open endpoint, and so that point is not included in the red line,
And
right?
so
So
is,
it's still only intersecting at that one place right there.
so do you have to write if it's a function or not anywhere?
It's not asking you that.
Okay.
It's not asking you that. Okay, but now what about the domain and the range? Okay, so the domain and the range of the piecewise function. Yeah, I need to pay attention, please. So for the domain, if I want to include the set of all the possible input values, then what is it? All real numbers, right? Because there's no gap in the domain, right? I mean, if an ant could walk along this function, it's like asking the question, for what x values could an ant walk on the function? There's no restriction. There's no x value the ant couldn't stand on. When he's on the red part of the function, he can walk to the left infinitely far, right? When he's on the blue part of the function, he can walk to the right infinitely far. And when the ant is at an x value of -1, he's standing on that point right there. Yep.
But what about the point -2, 1?
-2, 1.
That doesn't fit anywhere on the graph.
Well, no, but you're at -2, you're right, but at -2, he is standing on the graph, so that's part of the domain.
Oh, yeah, right.
You see what I'm saying?
I was thinking of full sets, not just domain.
Yeah, right, so the domain is everywhere defined. Now, what would have happened if, for example, we hadn't included that equal sign? And I had an open circle there and an open circle there. Then there would have been one x value that would have been restricted, that would not have been included in our domain, and what would that have been? -1. So we could have summarized that by saying x cannot equal -1. That would have been our domain. Because everything else is okay, but -1 wouldn't have been okay, right? Everybody with me?
what if it includes -1 on both?
Then it's not a function.
So don't bother.
Yeah, we're graphing functions, and so if this is a function, that can't happen because it would violate the vertical line test,
Okay.
okay? Now, what about the range, though? The range is gonna be a little trickier. Okay, greater than, okay, almost. You're close, but now let me see if you can answer what's wrong with that. So greater than or equal to -5 implies that every y value greater than or equal to -5 works. But what's the one that's not gonna, give me an example of one that doesn't work there? Why is that incorrect?
-1,
-4.5 is not a y value that's included in our range, is it? Right?
Where do we get 4 and 7?
It's because
Here, raise hands, Yep.
Would it be an or statement?
It's gonna have to be an or statement, yeah, because there's multiple, and why is it an or statement? Let's make that connection. It logically seems like, if here's a test you can apply. If I have to pick my pen off the board to graph the range, then it's gotta be an or statement. If I were just gonna graph the range, what would that look like? If I were just graphing the range, wouldn't I be graphing, I'd only be graphing that one point right there, or that interval, correct? That's a graph of the range. Everybody agree?
Yeah.
is it the same way for the domain if it's like
Hold that question for a second. Okay, so if I were to, now think what it means to graph the range again. Now we go back a little bit with this, right? The range is just the set of the y values for our graph, that are graphed, right? The output values for the function. How could we graph the range? We could project the graph onto the y-axis. If I were to project this graph onto the y-axis, all of the blue horizontal line only has one y value, doesn't it?
Yes.
It's gonna project onto the y-axis right there, isn't it? There's only one element of the range from that whole blue part piece of the function. The range is just y equals -1 for the whole thing, right? What about the red one, though? The red one, it's gonna be the range of the red piece is gonna be all values of y greater than -4, right? And so there's gonna be a little gap there, isn't there? When I graph the range, I've gotta pick my pen off the board to graph the range, and so it has to be an or statement, right? Anytime you have to pick your pen off to graph something, like a domain or a range, it means it has to be an or statement, because there's more than one part to it. And you can't be in two places simultaneously, the ant, right? The ant is either standing on this part of the range or on that part. It can't be two places at once, right? Question over here?
So let's say if the points were together.
Mhm.
that-
Then that'd be fine. If the points were together, then we could have said y is greater than or equal to
That
5.
would be an and.
That would be, right.
But because
It just would have been y is greater than or equal to 5. Yep, question. Okay. I mean, I know this is a little bit different, right? It's different kind of math than you're used to. Okay, so what would the range be then? How could we write the range? The range we could write as y equals -5, or y is greater than or equal to -4.
Wait, why is it equal to?
Not equal to, you're right, it's not equal to, my mistake, thank you. Oh, then. Okay, good?
No.
So the solutions, incidentally, I think the solutions use, they use kind of a set notation for this. And so this is just, I'm not gonna make you guys do this, but another way to write that would be this way. If I include the set of, the range as a set, I would write it like this. I would say, that means it's a set. And then I'm gonna declare whatever the variable is. So I would say it's the set of y values. And when I put a vertical bar like that, it means such that y equals -5, and I have to use a union. Y is greater than -4. Just so you've seen that notation. We don't have to do it that way this year. That's fine. It doesn't really bias anything. It's not.
I have no idea.
Wait, is that what you did? Why?
That's notationally, like, when you go to college eventually, your textbook might show it this way instead of this way. They mean the same thing, right? That's all I'm saying.
So like if you were to put that in, would you just?
Hey, you got too much, listen, I have to have you guys raise hands. I can't have all this talking, yeah.
So if you were to just put that in, like if you had to write it out on, Moodle, you would just use one of the absolute values, like.
You, then on Moodle, I would have you guys write it like this, if I wrote questions. I wrote some of these, but I didn't get them done in time to have them.
Yeah.
So I'm gonna have you guys do this homework on paper. It's- Now that I'm coaching basketball, my Moodle days may be a little bit more limited than they've been. I mean, a lot of the stuff's already built, but anything that's new that I've built, now that we're in basketball, that's probably not happening. So this one will be, it's gonna be here's your paper assignment on this one, right? Okay, let's go on, let's try another one of these now. Oh, okay, another one. How about this one?
Okay, I have a question.
Yep.
So, it's not a question, it's just a confirmation. So if it's a horizontal line, it's just equal?
Well, right, I mean, because if it's a horizontal line,
There's no
there's
slopes.
only one value.
Okay, thank you.
Okay, what about this one? Yeah, oh, and let's do this, okay, I'm gonna go about this a slightly different way. Okay, and I really need you to pay close attention to this, because I'm gonna say something that's really important here I want you to get. So this was like a technique that we used here. I want you to see that this makes sense, that we could have, one way we could do this is we could kind of lightly graph what the shape of that curve is gonna look like, and then only actually put my pen down and graph it in my domain, right? Another way of doing this, though, would be like if I wanted to, these are lines, and I wanted to graph the line y equals negative 3x in the domain x is less than 0. Well, that's a pretty easy one to do because I'm actually including the y-axis there. So that one we'll do first, and then let's do that one, and then we'll launch into another way of graphing the other two pieces without having to graph the whole line first. We could, but we don't have to. So for part A, that'll be our red piece of the function. I want you guys to tell me, how am I going to graph y equals negative 3x?
From the origin 0, 0.
Okay, so that's my starting point, is that the y-intercept is 0, 0, right?
You're gonna go right 1 and down.
Okay, I go down 3 and right 1, and I get another point there. And am I going to have an open or closed endpoint there?
You're going to have an
Open, good, it's going to be open, so I probably need to do this. Oh, I got an open endpoint, and I'm going to the right or the left?
The right.
What?
No, left,
To
sorry.
the left.
There's like
So I'm gonna line these up and I'm gonna go like that, right?
Yep.
Okay? Now, what about part 2? Part 2, it wants me to do the line,
So would that be a segment instead of a node?
No,
it's,
here.
no, it's not, because it goes, this middle one will be, you're right, middle one will be, absolutely, you're right. So the middle one now, that's gonna be blue.
Ooh, I like
The middle one is gonna be the line y equals negative 1/2 x minus 1. Okay, so where would I start that one? Negative 1, good, and open or closed endpoint there? Closed, okay,
Wait, right?
yep, right, because x is greater than or equal to 0. So because I've got that equal sign, it's gonna be closed, right? It's the left endpoint of this interval is gonna be closed. What do I do? Now, where do I go from there?
Down like over 2.
Okay, down 1 over 2. So down 1 over 2 to get another point, and I'll connect and extend those all the way up. How far do I extend those?
Till 6.
Till 6. So 1, 2, 3, 4, 5, 6. Okay, so I'm gonna extend it down to here, right, to this.
Down to 4.
So
Yeah,
I'm
down
going,
to 4.
there's 4, there's 6, right? So I go like that?
Yeah.
Everybody with me?
And then you do a closed.
And it's open there, everybody get that? It's open there because, look, I'm not including that endpoint, right? Okay, now here's the part, we'll look at the domain. The domain of the blue function is x is greater than or equal to 0. It's equal to 0, so I have to include that endpoint. And x is less than 6. So when x equals 6, that is not a point that's not in the blue domain, right? 6, turns out, is in none of the domains, right? There's no place up here where x ever equals 6.
That
right? Okay, now what about the last part though? Here's where I want to show you a little trick. So the last part, we'll graph this one, is going to be purple. Now, how do I graph that line? Well, I could go down to -7, or to 1, sorry, and then make a slope of -7 and just, sorry, to negative, I got it backwards, to -7 and have a slope of 1 and draw a line up from there, sorry, right?
You could go to 7 and put the point at 0.
Right, it's a good thing you're keeping track of me here. Okay, but I'm not gonna do it that way. Let's do it a different way. Let's do this with a little t-table, because we could kind of divide this up, couldn't we? We've got the blue domain, the blue-red transition is right here, isn't it? Right, so everything from that x value up to, but not including this x value, is where the blue function was graphed. Everything to the left of that is where the red one is graphed. The purple one is going to be graphed up there, isn't it? In this part of the graph. Everybody agree? Because the purple domain is x is greater than 6, right? Okay, so here's a tricky way to do this. We could make ourselves a little purple t-table. How many points are required to graph a line? 2, right? So I only need 2 ordered pairs to get the purple line. Well, why not pick 2 ordered pairs where the purple line lives, which is for x values greater than 6, right? So let's just come down here and we're going to make a little t-table, x, y, and let's pick values that make sense, like 6, how about? If I pick x equals 6, what's the y value I'm going to get back from the purple function? -1, right? Everybody agree with that?
Yep.
So when I plug 6 in, I'm going to get the point -1, so there's an ordered pair. Now, at 6, I'm at the end point, but I'm not actually including that point, am I? So it's going to be an open circle, so that one's going to be open. So we'll go over to 6 and down to -1, and I'm going to make an open circle. Well, we just need one more, but let's pick another one that's in the purple domain that's a value greater than 6. So why not 7, right? 7 is a compatible number there that's not going to give us a fraction, right? So we'll pick 7. If x equals 7, what does y equal? 0. Okay, so we've got the point 7, 0, which is right there, and now we can just do that.
But you know the slope is 1 anyway.
Right, we did, but I'm making a point here. I want you to see that we could always just generate 2 convenient points. Question?
The first one would be
Right, because it's not included? Okay.
So then would the domain be all reals if provided x doesn't equal 6?
So the domain, well, we'll get to that. We'll get to that. What if I wanted to use that trick in the middle function? I just want to make a quick point here. Like, what if I wanted to make a blue t-table to pick points in here? I didn't need to, right? Because we were able to use the point slope method because x equals 0 was the edge of our domain. So it made sense just to use the y-intercept. But what if it didn't? What if the blue domain were somewhere else? I could have done the same thing. I could have made a blue t-table. And I would have wanted to pick what kinds of numbers for x to make the math work out well.
Even numbers.
Even numbers, because I'm multiplying x times 1/2. You see my point? I want to pick compatible numbers when I'm using this technique, if I can. So I could have picked numbers like 2. 2 is a good one because that's going to give me -1/2 times 2 is -1 minus 1. I get 2, -2, right? And I might have picked like 6, right? Or 4 would have worked. If I pick 6, I'm going to get -3 minus 1 is -4. Those would have been 2 convenient points that would have worked for me, right? Okay, so what about the domain then? We just got to let's make the journey, let's make the ant's journey from -infinity to infinity. You tell me if there's any x values that have to be excluded. Well, 6. We're fine to there, but there's our problem, right?
That's so
So it's-
sad.
Okay, so the domain is going to be then x cannot equal 6. Okay, now if I wanted to write that using like interval notation,
So it's
I'd have to do something like this,
All reals except for 6.
right?
and then 6, comma.
I'd have to do that. But isn't it a lot easier just to use inequality notation and write x is not equal to 6? right? Because what does that imply? If the domain is x is not equal to 6, it
It's
implies
all-
everything else is fine,
Yeah.
right?
Yeah.
Okay? What about the range?
It's,
No,
no,
don't say it out loud, I want people to get a chance to think about this a little bit.
one,
So if I'm gonna map this thing onto the y-axis, I'm gonna graph the range, right? I wanna graph the range here, so what's that gonna give us? We're gonna get,
x is greater than -4.
Y,
sorry.
everybody agree with that? So the bottommost value, the bottom edge of the range is gonna be this part right here, right? So we're gonna get an open circle on the y-axis, and then we're just gonna keep moving up. We get to there, and that's included, but then look, everything above that is also included, because we make a transition from the blue part to the purple part, so the y's never stop, do they? They keep going up, and then here the y's overlap anyway, and so there's no other y value that ever gets skipped, right? All the y values are included above -4. So the domain would be y is greater than -4.
Yeah.
Okay, get the idea?
Yes.
Okay? That's a lot of stuff, right? So there's one other piece I didn't get to. I don't wanna do it today, though.
So we don't have homework?
So, yeah, you can do everything on the homework except the last problem you can do.
Okay.
Number 12, I'll talk
But do
about
we
tomorrow.
have to do it?
Yes. Yeah, once you
Great.
do this one.
Great.
And let's say, I'll turn that in, how about Thursday?
I won't be here,
Okay.
so tomorrow?
Then, or when you get back.
I'll be on some, I can.
Okay.
Oh.
Why?